Okay, we're going to try to use what we've learned the past few lessons to find prime numbers, to figure out if a given number is prime or composite. First, we'd like to watch this. I'm going to see if I can play it on here. If not, I may need to link it to your Google Classroom. Nope, I can't. Please watch. I'll link it to your Google Classroom and you can play it. It's pretty short and sort of fun. Okay, so we're talking about prime numbers, and the video that you should have just watched, it introduces you guys to encryption and huge numbers. So encryption algorithms are the basis of all secure internet transactions. Today, a lot of encryption algorithms rely on very large prime numbers or very large composite numbers that are the product of two prime numbers to create an encryption key. Often these numbers are Mersenne primes, which are primes of the form 2 to the p minus 1, where p itself is prime. But interestingly, not all numbers in this form are prime. As of December, 2013, only 43 Mersenne primes have been discovered. So if you get a chance, just Google these things and, you can look into them and learn about the importance of prime numbers. Mathematicians have tried for centuries to find a formula that will always yield prime numbers, but have been unsuccessful. The search for large prime numbers and a formula that will generate all the prime numbers has provided fertile ground for work in number theory. Pierre de Fermat, which is a mathematician from the 1600s in France, he applied the difference of two squares identity to factor very large integers as the product of two prime numbers. And that's what we're going to do today. So up to this point, you guys have worked with numbers that can be expressed as the difference of two perfect squares. And if a prime number could be written as the difference of two perfect squares, then it would have to be a plus b, a minus b, okay? Where a and b are consecutive numbers, and a plus b is prime. The challenge is that not every pair of consecutive whole numbers yields a prime number when added. For example, 3 plus 4 is 7. We have a prime number and a composite number. And then 4 plus 5 is 9. Here we have a prime number, here we have a composite number. So consecutive numbers, but I get a prime here and a composite there. Okay, opening exercise. You'll see on your worksheet, complete the table to investigate which numbers of the form 2 to the n minus 1 are prime and which are composite. So you have all the n's. Go ahead and fill in 2 to the n minus 1. So this first one will be 2 to the 1 minus 1, which is 1. Okay? 2 to the 2 minus 1 is 3. This is prime, prime. I'm going to push pause and fill in this table. Okay, there's our first page. Go ahead and push pause and see that you got the same answers, and then you can move on to the next page and we'll talk about it. Okay, what patterns do we notice? I've got lots of primes, composite prime, composite prime. This is prime, 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 composite prime. Composite prime. Does that lead to a pattern? Well, that does. If we compare this with that. Let's look at the next page. Push and pause again. Awesome. So what patterns do we notice in this table about which expressions are prime and which are composite? I'm going to go back one. Let's see. I have composite, 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 prime. Ooh, there. That one broke our pattern. Really, there is no pattern. I thought there was until that last one. Okay, let's talk a little bit more about the patterns that we notice about the expressions and which ones are prime and composite. We said that we didn't really see a pattern. So how about when the exponent, when the exponent was an even number, greater than 2, okay, an even number greater than 2, not greater than or equal to, the result was composite. And it can be factored. Using 2 to the 2n minus 1, which is 2n plus 1. Let me rewrite that. I didn't leave enough space. 2 to the 2n minus 1 is 2 to the n plus 1, 2 to the n minus 1. Okay? When the exponent is a prime number, the result is sometimes prime and sometimes not prime. I'm just writing this down so you can write it down too. For instance, 2 to the 11th minus 1 was the first one that gave me a composite answer. Result was composite, even though my exponent was prime. Okay, one more. When the exponent is a composite, odd number, the expression appears to be composite, but we have yet to prove that. You can't prove that with just 11 samples. Okay? These are all examples of the types of patterns that we're going to notice as we complete the opening exercise. Okay? So let's go ahead and try. Okay, so let's talk about this. So this example and the next exercise prove patterns that are important. We need to notice, it proves the patterns that we noticed in the table in the opening exercises. So let's just read through it. We're going to read through the conjecture and try to form a pattern. So let me get the highlighter out. So our conjecture, if m is a positive odd number, then 2 to the m minus 1 is a composite number. Okay, so we're going to start with our identity. This right here equals x minus 1, x to the n minus 1, n minus 2, etc. Okay, we use this identity for quite a few lessons so far this year. In this case, if x equals 2, the identity becomes 2 to the m minus 1. So we get 2 minus 1, doing that right here, times 2 to the m minus 1, 2 to the m minus 2, etc., etc., until we get to the constant at the end. Equals 2 to the m minus 1, 2 to the m minus 2, etc., etc. It's important to point out 2 minus 1 disappeared because 2 minus 1 equals 1. Okay? It's not clear whether it's composite or not, because composite just means I've got a factor times a factor. But when my first factor is 1, I don't know if it's composite or not, because anything times 1 is by definition a prime number. Okay, so that doesn't really help us. So let's try rewriting the expression. Let m, in this example, be AB. Let m equals AB be a positive odd composite number. Then A and B must also be odd, or else the product AB would be even. So let m equals AB be a positive and odd, I wrote D, be a positive and odd composite number. Positive, odd, composite number. That would be like, I don't know, 15 is a positive, odd, composite number. Okay, we'll get an example that gives us another number, but I was just giving you an example. The smallest, there we go, the smallest such number is 9. So we have A is greater than or equal to 3, and B is greater than or equal to 3. Okay, let's try it. All right, so we have the same beginning as we had up here. And that gives us, so we know M is A times B. So let's just go here. 2 to the A to the B minus 1. So we have 2 to the A minus 1 times 2 to the A, B minus 1, etc. Let me erase that. That got a little messy. So for this first term, B is 1. So that's why it's just 2 to the A. So then we have 2 to the A, B minus 1, 2 to the A, B minus 2, etc., etc., etc. So this will give you some number larger than 1. Since A is greater than or equal to 3, we have 2 to the A is greater than or equal to 8. So 2 to the A minus 1 is greater than or equal to 7. I just subtract 1 from both sides. Okay, since this is larger than 1, 2 to the m minus 1 is composite. Since it's larger than 1, if I have two factors, so we have factor times factor, neither one of those factors can be 1. So since it's larger than 1, it has to be composite. Because when we do a composite number is a factor times a factor, neither one of those factors can be 1. It has to be larger than 1. Because that's the definition of a composite number. If it were 1, that's the definition of a prime number. All right, exercises 1 through 3. So for these exercises, find a factor of each expression using the method discussed in example 1. Let's actually work through one, and we'll try to make that last slide make better sense. Now remember, we're using this 2 to the m minus 1, where m equals AB. Okay? So we have to try to figure out what to do with this. I need two numbers multiplied times each other. And it has to be a power greater. It's easier if it's a power greater than 2. So we're just going to go 2 to the 5th. And if I make that 2 to the 5th, what power do I make it raised to? It would be 3, because 3 times 5 is 15. Minus 1, which gives us 2 to the 5th minus 1 times 2 to the 5th squared minus 2 to the 5th to the first power, this is plus 1. So this term right here is not 1. 2 to the 5th is 2 times 2 is 5. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 64. Minus 1, I did that wrong. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Goodness, let's do some math here. 32 minus 1 is 31, times, I don't really care, it's greater than 1. And that's the point. Okay, let's try the next one. I need to change that into 2 to the, let's make it easy on us, 2 to the third. 3 times what is 99? Minus 1. So let's get, we just want to make sure our first term isn't 1 and our second term is greater than 1. So we have 2 to the third minus 1 times 2 to the third to the 32nd plus 2 to the third to the 31st, etc. This is greater than 1. We're good. This is 8 minus 1, which is 7. So, since 31 is a factor, this is composite. Since 7 is a factor, this is composite. I want to point something out. In the previous slide, we said that m equals ab must be a positive, odd composite number. Okay, a positive odd composite number. So A and B have to also be odd. When we pick our A's and our B's, they must also be odd numbers, or else the product would be even. Okay, so as we pick our numbers to mess with these powers, we need to pick 2 odd numbers, and this only works if our power is a positive odd composite. Let's try this next one, okay? Hint, 537 is the product of 2 prime numbers that are both less than 50. If you grabbed your calculator, you can figure out, just take 537 and start dividing by prime numbers that you know. So don't kill yourself to get really big ones. Start with 11, then try 13, then try 17, but we're going to get 17 times 31. So I'm going to push pause. Just try this one on your own and then check your answer. Okay, we're good. I mean, I picked 17 and 31, which we said beforehand. This first term is a number. It's a number greater than 1. The second term is also a number greater than 1. We don't have to calculate it. We know that if this is a valid number, then it is, in fact, composite. This little symbol here means therefore. Therefore, it's composite. All right. A few little cool things. Cryptography is the science of making codes. And cryptanalysis is the science of breaking codes. Pretty cool. Random information. So RSA encryption uses very large numbers with hundreds of digits that are the product of 2 primes. The product of the prime factors is called the key. The key itself is made public, so anyone can encode using this system, but in order to break the code, you would have to know how to factor the key, and that is what is so difficult. Okay, you may have Googled RSA in a previous slide, which I'd asked you to do if you have time. So exercise 4, the logic. The logic behind modern encryption algorithms. How long would it take a computer to factor some squares of very large prime numbers? The time in seconds required to factor an n-digit number of the form p squared, where p is a large prime, can roughly be approximated by that really big function. Some values of this function are listed in the table below. We're looking at time here. So if this is p, as a very large prime number, it's going to take 3,400 seconds to decode that number. Use the function given above to determine how long it would take this computer to factor a number that is 32 digits. So here we have 9 digits, 11 digits, 13, 15, 17, 19, if we had 32 digits. So let's plug in some numbers. I have f of 32. Oops. 32. So I'm using this function right here. 3.4 times 10 to the n is 32. 32 minus 13 over 2. I don't have my calculator out, so let me simplify and then I'll get my calculator out. 32 minus 13 is 19 over 2. You can actually type that into your calculator just as you see it. Make sure you put parentheses around here if you need to, and you get an answer of 1.08 times 10 to the 10th seconds. That is actually about 342.5 years. Yikes. That's crazy. So that's too long to factor a 32-digit number, making any secret message encoded with that number obsolete before it could be cracked. Like if you finally crack the code, it's obsolete. Like you never need it anymore. However, we have extremely fast computers and very efficient algorithms designed for those computers for factoring numbers. These computers can factor a number thousands of times faster than the computer used above, but they're still not fast enough to factor huge composite numbers in a reasonable amount of time. All right, go ahead and read this, and then I'll talk about it. Push pause. There's just interesting information that I thought I'd include that was in my book and not yours. So, in closing, summarizing what we've learned, there are better ways of factoring numbers than just checking all the factors. But even with advanced methods, this takes a long time to execute. Products of primes of the magnitude, like if we did 2 to the 2048, are almost impossible to factor with a reasonable amount of time, which is how mathematicians are guaranteeing the security of electronic transactions, the encoding. We know that what we do electronically is safe because of these prime and composite factors. So first of all, we learned that polynomial identities can help us prove conjectures about numbers and make calculations easier. And then the field of number theory has contributed greatly to the fields of cryptography and cryptanalysis. It's just a really, really, really cool branch of mathematics. People do this for a living, which is just fascinating to me. That's all we have.